Valence bond theory is particularly useful in explaining molecular geometry. And to do this, we use a concept known as orbital hybridization. Let's illustrate that with this example right here, acetylene, okay, C2H2. This is the Lewis structure for acetylene. You have a triple bond between the two carbon atoms, and each carbon atom is a single bond with a hydrogen. Now, so the sigma bond, the first bond between these two carbon atoms, okay, is a sigma bond, and then the two other bonds would be a pi bond. So because the shape, we predicted the shape of this molecule, and experimental observations corroborate that prediction, that this HCH angle is 180 degrees. Okay, that means this sigma bond between these two carbon atoms and this sigma bond between the carbon and the hydrogen atom are oriented 180 degrees apart. Okay, so how do we explain that? Well, first of all, the second and the third bond between these two the two carbon atoms, we said, if you remember, we said earlier, is due to pi bonding, right? So we say it's due to overlap between neighboring p orbitals. So you might have a px orbital on this carbon and a px orbital on this other carbon. The overlapping of those two gives rise to one of the two pi bonds. The other pi bond comes about when you have an overlap between the py orbital on this carbon and the py orbital on the other carbon. Okay, so that takes care of the two pi bonds. So in other words, we're assuming here that this is our z-axis, okay, and then your x-axis would be this way, and your y-axis would be this way. All right, so now let's explain the sigma bonds. Why are those sigma bonds 180 degrees apart? The way you explain it is this. Okay, think about the carbon atom. A free carbon atom, we said, in its valence subshell, okay, in valence shell, has a 2s and a 2p subshell, right? So 1s2, 2s2, 2p2. It has 4 electrons in the valence shell. Okay, so if we draw the orbital diagram, you would have something like this: 1s, 2s, 2p. Remember, a 2p subshell consists of 3 orbitals, and so you have 2 electrons in the 1s, 2 electrons in the 2s, and then 2 electrons in the 2p orbital. Okay, only the valence orbitals are going to be involved in bonding, right? The inner electrons are not involved in bonding. So you've got 4 electrons in a valence shell, but only 2 of those are unpaired. So how can carbon end up having 4 pairs in a molecule? Then we try to explain that by saying, okay, it must be that before the bonds are formed, one of these electrons in the 2s must have transferred over to the 2p. Okay, so what happens then? Well, so we say now our orbital diagram for the carbon atom in the molecule would now be, for the valence shell, would have 1 electron in the 2s and 1 electron in each of the 2p orbitals. Okay, and we say we can take into account, okay, 2 of the pairs as being due to involving the 2px and the 2py. So the 2 other pairs that the carbon must be using for a sigma bond must be the 2s and the 2pz orbital. Okay, so the explanation for the 180 degree angle between the two sigma bonds is as follows. You say that this 2s and this 2p orbital no longer exist in the molecule. Okay, so instead of having a 2s, 2pz, 2px, and 2py, okay, in the molecule, the carbon atom now has a pair of hybrid orbitals. Okay, it uses a hybrid of the s and the 2s and the 2pz orbital to create for bonding with other atoms in this particular case. So what we're saying then is, okay, so here's, remember an s orbital is spherically symmetrical, right? And a 2pz orbital, if this is your z-axis right here, would be positive on one side and negative on the other side, right? So let's just say it is positive on this side. Let me color code this. Let me do this again. Alright, so let's say the 1s is positive. Alright, so the 2pz orbital is positive on one side, negative on the other side. Okay, so we say that instead of a 2pz and a 2s orbital, what you end up having in the molecule are two hybrids. So when you have when you add these two, okay, then what ends up happening is when you add this 2s and the 2pz orbital, what ends up happening is that on this side of the nucleus, on this side, on the left side, you have destructive interference. So the resulting hybrid orbital would have a very low amplitude on one side of the atom, and these the positives would reinforce on the other side. On this side right here, you have positive reinforcements. You have constructive interference here. Constructive interference of the wave functions. So you have a high density, high probability of finding the electron there now. And then the other possible hybridization is one where you subtract. So now if you subtract, so this essentially becomes positive and the other side becomes negative. So your hybrid orbital will now have a high electron density on one side as opposed to the other side. Now these two hybrid orbitals would be directed 180 degrees apart. Okay, so we then say that one of these hybrid orbitals, the one that's pointing to the left, is going to overlap with the 1s orbital of hydrogen. So if I have a 1s orbital from hydrogen right here, and we have the sp orbital from the carbon, that overlap gives rise to one of the two sigma bonds, this CH bond right here. So we say that this is an S to sp overlap. Okay, S to sp overlap. The s orbital of a hydrogen overlaps with an sp hybrid from carbon. That accounts for that sigma bond. And the other sigma bond right here is an sp orbital of this carbon right here overlaps with the sp orbital of this other carbon right here. So this other carbon also undergoes sp hybridization in this particular molecule. So that's how you would explain the bonding in acetylene using valence bond theory.